Welcome to the Curious Voyager. It's lovely to have you here tonight. Wherever you are right now, whatever corner of the world you've carried this little voice into, I'm glad you came. Maybe you're under a heavy blanket with the lamp still glowing low beside you. Maybe you're on a couch with your shoes still on, not quite ready to admit the day is over. Maybe you're on a late train, the window dark, the city sliding past in smears of orange light. It doesn't matter. You found your way here, and that's enough. Settle in. Let your shoulders come down from wherever they've been hiding all day. Before we begin, let me say one small thing, and then I promise I'll let you drift. If you enjoy these slow journeys, if you'd like more nights like this one, a gentle like and a subscribe really does help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you already here, already part of the quiet ritual, returning night after night, thank you. Truly. I think of you out there, scattered across time zones, all listening to the same soft voice in the dark. And it's a lovely thing to picture. So tell me, if you feel like leaving a word before you fade off, where in the world are you listening from tonight? And what time is it in your corner of the night? I always love to imagine the map of us. There, that's done. Now you can let go. Here's how tonight will go, and I want you to hear this part clearly because it's a kind of permission. We are going to move slowly, slower than you're used to, probably. We're going to take one strange and beautiful idea, and we're going to walk all the way around it, gently. The way you'd walk around a sleeping animal you didn't want to startle. There is no rush. There is no test at the end. You do not have to follow every thread. If you drift off somewhere in the middle, and I rather hope you do, that's perfectly fine. The story will still be here when you wake. The ideas don't go anywhere. They've waited more than 100 years already. They can wait for you. And I'll try, as I always do, not to make this so interesting that it keeps you awake. Though if it does, if some small piece of it lodges in your mind and follows you down into sleep, well, at least you'll have learned something. A fair trade, I think. So, tonight's story. I want to begin not with a great triumphant moment, not with a man standing on a stage to thunderous applause, but with a confession. A quiet, private, almost embarrassed confession, written down by an old man late in his life, in a letter to a friend across the ocean. The year is 1931. An aging physicist sits at his desk in Germany. He is 73 years old by then, and he has lived a very long life, and he has, by any measure the world might use, won. He has a prize that bears the highest honor his field can give. There is a fundamental constant of nature, one of the deepest, most unshakable numbers in all of physics, that carries his name and will carry it forever as long as anyone anywhere studies the universe. His name is stitched into the fabric of reality itself. And yet here he is writing to a man named Robert Williams Wood, an American physicist, a friend, and he is trying to explain something that has clearly haunted him for 30 years. He's trying to explain how he came to do the thing that made him immortal, and the words he chooses are not the words of a proud revolutionary. They are not the words of a man who set out to change the world and succeeded. He calls it an act of desperation. That's his own phrase. In his own language, it's even starker, an act of Verzweiflung, an act of despair, of desperation, of being at the very end of one's rope. He writes, more or less, that he had been ready to sacrifice any one of his previous convictions in physics to get a result, that a theoretical explanation simply had to be found at any price, however high that price might turn out to be. He had reached a point where he would give up anything he believed, anything he held dear about how the world worked, just to make one stubborn equation come out right. Now, sit with that for a moment because it's strange, isn't it? We're talking about a man who discovered something so important that it opened an entirely new age of physics. And his own description of how he did it is the language of a man who was cornered, trapped, out of options. A man doing something he didn't want to do, didn't fully believe in, and would spend the rest of his life quietly wishing he hadn't had to do at all. That's the heart of the story I want to tell you tonight. Not the story you may have heard where a bold genius peers into the unknown and pulls out a revolution with a confident hand. The truer story, the stranger, sadder, more human story, is almost the exact opposite. It's the story of a deeply conservative man, a traditionalist, someone who loved physics precisely because he thought its great truths were eternal, settled, unbreakable, and who was forced, against everything he believed, to introduce the one idea that would quietly shatter that eternity, and then spent more than a decade of his life trying to take it back. This is the story of the reluctant revolutionary, the man who broke classical physics and refused for years and years to believe that he had done it. His name, of course, was Max Planck. Let me tell you about him slowly before we get anywhere near the equation that broke his world. Because to understand why that confession matters, why an old man would still be wincing at his own greatest achievement 3 decades later, you have to understand the kind of man he was before any of it happened. You have to understand what he loved and what he believed, and why this particular idea, of all ideas, would feel to him like a betrayal of everything he held sacred. He was born Max Carl Ernst Ludwig Planck on the 23rd of April in the year 1858 in the city of Kiel, up in the north of what was then a patchwork of German states near the cold grey water of the Baltic. A long name for a man who would become known simply, eternally, as Planck. He came from a family of the old, serious, respectable kind, a line of pastors and lawyers and scholars, people who believed in order, in duty, in the deep value of doing things properly and well. That sense of order soaked all the way through him. It was in his bones. He was, throughout his whole life, a deeply formal man, devout in his faith, precise in his habits, the sort of person who valued tradition not as a cage, but as a comfort, as the accumulated wisdom of everyone who came before, something to be honored rather than overturned. He loved music too. He was a gifted pianist, and he carried a kind of musical sensibility into everything he did. There was a reverence in him, a reverence for the idea that some things are true and lasting and beautiful precisely because they do not change. And nothing embodied that reverence for him quite like physics. You have to understand what physics felt like to a young man like Planck in the latter half of the 19th century. It felt almost finished. It felt like a cathedral that was very nearly complete. The great architecture was all in place. Isaac Newton, 2 centuries earlier, had given the world its laws of motion and its law of gravity, a clockwork universe, predictable and continuous, where if you knew where everything was and how fast it was moving, you could, in principle, calculate the entire past and the entire future. Everything flowed smoothly, nothing jumped, energy poured and shifted and changed like water, in any amount you liked, in unbroken streams. And on top of Newton's foundation, the 19th century had built more, the laws of heat and energy, thermodynamics, the great unchanging principles about how energy moves and spreads and can never be created or destroyed. And James Clerk Maxwell had wrapped up light and electricity and magnetism into one gorgeous, elegant set of equations that seemed to explain it all. The cathedral was nearly done. The roof was on. There were just a few small details left, a bit of trim here, a loose thread there, just tidying up. This is the world young Max Planck wanted to step into. And here is the first piece of irony, the first thread of the story that will wind all the way through to the end. So hold on to it gently as you drift. When Planck was a young man trying to decide what to study, he went, by some accounts, to ask the advice of a physicist named Philipp von Jolly in Munich. And Jolly told him, and I want you to really hear this because it's one of those small moments that history loves to circle back on. Jolly told him, more or less, not to bother. That physics was essentially a complete science, that all the great discoveries had already been made, that the fundamental laws were known, the structure was finished, and there was nothing important left to find. Only minor details remained, small holes to be filled in, decimal places to be refined. A young man with ambition, Jolly suggested, would be wasting himself going into a field where all the great work was already done. Imagine being told that. Imagine being a young person standing at the start of your life full of quiet hope and having an experienced elder tell you kindly enough that you've arrived too late, that the feast is over, that there's nothing left for you but to sweep up the crumbs. And here is Planck's reply, and it tells you everything about who he was. He said, and this is documented in his own scientific autobiography, in his own recollection, that he did not in fact wish to discover new things. He didn't want to be a great discoverer. He had no hunger to overturn the established order or to make some startling new finding. All he wanted, he said, was to understand the fundamentals that were already known, to grasp the deep, settled, eternal truths of the physical world more clearly. That was his ambition. Not to break new ground, but to stand on the ground that was already there, and to understand it perfectly. Let that sit in the dark with you for a moment, because this is the man, this is exactly the man. He didn't want to be a revolutionary. He said so out loud at the very beginning. The whole appeal of physics to Max Planck was that it seemed eternal and absolute and done. He wanted to live inside its finished cathedral and run his hands over its old stone walls and understand, deeply and quietly, why each stone was placed where it was. He wanted permanence. He wanted certainty. He wanted the comfort of things that do not change. And the universe, as it tends to do, had other plans for him. Now, I don't want to rush ahead. We have all night. And the best part of a story like this is the slow building, the way the pieces line up before they fall. So let me just hold us here for a little while in the world before the break so you can feel how solid it was, so you can feel what it was that he stood to lose. Picture that 19th century physics as a kind of beautifully ordered house. In that house, everything is continuous. That's the key word, continuous. It means smooth, unbroken, infinitely divisible. Think of pouring water from a jug. You can pour a lot or a little. You can pour a trickle so thin it's almost nothing, and then a trickle even thinner than that, and there's no smallest possible amount of water. You can always, in principle, pour just a little less. Energy in the classical world was like that water, smooth, continuous. You could have any amount of it you liked, in any quantity, sliding seamlessly from more to less, with no gaps, no steps, no jumps. A heated object glowed because it was shedding energy, and it could shed that energy in any amount at all, in a perfectly unbroken stream. That smoothness wasn't just a detail, it was the whole spirit of the thing. It was Newton's smoothness, the smoothness of planets gliding along their orbits, of a thrown ball arcing through the air, of a pendulum swinging down and up. Nothing in the classical universe ever jumped from one state to another without passing through everything in between. Reality was a continuous, flowing, predictable thing. Cause led smoothly to effect. If you knew enough, you could predict everything. It was determined, it was orderly, it was, in a word that meant a great deal to a man like Planck, lawful. And there was a deep, quiet comfort in that. There still is, honestly, in the idea of it. A universe that flows smoothly, where everything connects to everything else by unbroken chains of cause and effect, where there are no sudden gaps and no dice being thrown in the dark. That's a tidy universe, a trustworthy one. The kind of universe a careful, devout, orderly man could build his life's understanding upon and feel that the ground beneath him would never shift. That was the world Max Planck loved. That was the cathedral he wanted to spend his life understanding. He never wanted to tear it down. He never even imagined that it could be torn down, least of all by his own hands. But there was a problem in that cathedral. A small one at first. The kind of loose thread that Philipp von Jolly might have waved away as one of those minor details left to clean up. It had to do with light, with heat, with the glow that comes off of warm things. We'll get into the heart of that problem soon. Slowly, gently, with all the time in the world. But I want to plant the seed of it now, here in the calm before we begin, so that you carry it down with you. Because it's a question so simple that a child might ask it, and yet the answer to it would crack the whole foundation of physics open. The question is this: when you heat something up, when you make it hot, it glows. You know this, you've seen it. The coil of an electric stove going from dark to a deep, dull red as it warms. The metal in a toaster flushing orange. A bar of iron in a blacksmith's fire climbing from red to orange to a fierce yellow-white as it gets hotter and hotter. The hotter the thing, the more it glows, and the color of the glow shifts, climbing up through the colors as the temperature rises. Everyone knew this. It was utterly ordinary, the most everyday thing in the world. But here is the trouble. When the physicists of the late 19th century, Planck among them, sat down with all their beautiful, finished, continuous classical physics and tried to use it to explain exactly how much light of each color a warm object should give off, to predict the glow precisely with their equations, the answer their physics gave them was not just wrong, it was insane. It was a catastrophe. It was an answer so absurd that if you took it seriously, it meant that every warm object in the universe, every kettle, every candle, every coal, your own warm body lying there in the dark right now, should be blazing with an infinite amount of energy, should be pouring out a limitless, universe-incinerating flood of light, which you may have noticed you are not doing. You are lying there quite peacefully, glowing only faintly with the gentle warmth of a living thing, very much not setting the cosmos on fire. Classical physics demanded the impossible. The finished cathedral had a crack in its foundation, and the crack, when you look closely, went all the way down. And the man who would be forced to deal with that crack, and the man who would, in the end, be the one to climb down into the dark of it and find that the only way to seal it was to introduce an idea so radical it would bring the whole continuous, smooth, lawful, eternal universe crashing down, was the one man in all of physics who least wanted such a thing to be true. The traditionalist, the conservative. The man who had told Philipp von Jolly that he didn't want to discover anything new, that he only wanted to understand the eternal truths that were already there. That's the irony I want you to carry into your sleep tonight, like a small, warm stone in your pocket. The man who broke classical physics revered classical physics. He loved it the way you love something you believe will last forever. And the breaking of it would cost him, emotionally, intellectually, philosophically, more than almost anyone could understand. He didn't celebrate it. He mourned it. He spent years, more than a decade, trying to undo it, trying to put the cathedral back the way it was, trying to prove himself wrong. He failed. The universe really was as strange as his desperate equation said it was. and the proof of just how strange would come in time from others. From a young patent clerk named Albert Einstein, who would take Planck's idea far more seriously than Planck himself ever dared, and from a young Dane named Niels Bohr, who would use it to rebuild the very atom. We'll meet them later, in their own good time. For now, just hold the shape of the thing, the reluctant father of a revolution he wished had never happened. How does a careful, conservative, order-loving man end up doing the most disorderly thing in the history of his science? How does the man who wanted only to understand the old truths end up writing the equation that ends them? And why? This is the question that Letter to Robert Williams Wood leaves hanging in the air. The question we'll spend the night gently answering. Why would he call the greatest achievement of his life an act of desperation and mean it and go on meaning it for 30 years? We'll get there. Slowly. Step by step. There's a whole century-old room of physicists waiting for us in a city called Berlin, with their delicate instruments and their careful measurements of glowing things. And they're part of the story too. There's an institute full of people whose actual job, believe it or not, was something as humble as figuring out how to rate the brightness of light bulbs. And the quantum, this deepest idea in all of modern physics, this idea about the very graininess of reality, was born partly out of that, out of a lighting problem, out of someone needing a good way to measure lamps. Isn't that something? The grandest revolution in the history of physics, with one foot quietly planted in the business of selling light by the bulb. But all of that can wait for the next stretch of our journey. For now, I just want you to rest in the strangeness of the beginning. A man is born in a grey northern city in 1858. He grows up loving order and permanence and the eternal truths of a finished science. He is told, as a young man, that there is nothing left to discover. He says that's fine. He never wanted to discover anything anyway. He only wanted to understand. And then, through no ambition of his own, through nothing but a stubborn refusal to let one small problem go unsolved, he stumbles into the deepest crack in the foundation of the world and finds that the only way to seal it is to break everything he loves. And when he does it, when he finally, reluctantly, desperately does the thing that has to be done, he doesn't believe it. He can't believe it. He decides it must be a trick, a temporary patch, a mathematical sleight of hand he'll explain away properly in the old continuous language just as soon as he has the time. He never does explain it away. It was real all along. That's where we're headed, but there's no hurry at all. If your eyes are already heavy, let them close. If you've lost the thread already and you're just floating on the sound of the words, that's perfectly good too. None of this is going anywhere. The old physicist at his desk in 1931 wincing at his own immortality. The young man being told that physics is finished. The crack in the cathedral floor glowing faintly in the dark, waiting for someone careful enough and desperate enough to climb down into it. They'll all still be here. Let yourself sink a little deeper into wherever you're resting. Feel the weight of your own warm body, glowing faintly with its own gentle heat. Not setting the universe on fire after all, held back from that classical catastrophe by some hidden grain in the structure of reality that we'll come to understand together, slowly in the hours ahead. There's a comfort in that, I think, that you lying there are a small living proof that the old physics was wrong and that the strange new truth, Planck's reluctant, desperate, beautiful truth, is what keeps you from blazing away into infinity. The quantum is the reason you can lie in the dark and simply be warm, simply be at rest. So rest. We have a long, slow, gentle journey ahead, and we're going to take every bit of it at the pace of someone with nowhere to be and nothing to prove. We'll wander through Berlin and its careful measurements, through old equations that worked beautifully right up until the moment they catastrophically didn't, through one evening when a colleague named Rubens came to Planck's house with a handful of numbers that would set the man working long into the night. We'll find the equation. We'll find the tiny, tiny number hidden inside it, a number so small it has 33 zeros tucked away after its decimal point, small enough to hide an entire revolution in the grain of the world. And we'll find the man, again and again, refusing to believe what his own mathematics was telling him. But that's all ahead. For now, there's just the beginning, and the dark, and the soft sound of a story being told slowly. A man who loved a finished world, a crack in its floor, and the long, reluctant night in which he finally went down to seal it, and broke it open instead. Breathe. Settle. Let the warmth of the story hold you. Out there, scattered across all your different corners of the night, we're all drifting through the same strange and gentle tale together. The tale of how the most certain world anyone had ever known quietly came undone at the hands of a man who only ever wanted certainty. There's something soft in that, something almost tender. The universe is far stranger than the old physicists hoped, and somehow, knowing that lying here in the dark, it doesn't feel frightening at all. It feels like wonder, the good kind, the kind that loosens the shoulders and slows the breath and asks nothing of you but that you marvel gently and let go. We've only just begun. There's so much more to come. The room full of glowing instruments, the catastrophe in full, the desperate equation, the tiny number, the long years of a man trying and failing to take it all back. We'll get to every piece of it, unhurried, with all the time in the world. But for now, just stay here a moment longer with the young man in Munich, standing before his elder, being told that physics is finished, that there's nothing left to find. Stay with him as he answers, quietly, that this suits him fine, that he never wanted to find anything new. He only wanted to understand. He had no idea at all what was waiting for him. No idea that the very wish to understand patiently, completely, refusing to leave even one small problem unsolved, would lead him straight to the deepest, most disorderly, most revolutionary idea anyone had ever had. That his love of the finished, eternal, continuous world would be the very thing that ended it. The reluctant revolutionary. Hold that close as you drift. We'll follow him down into the crack together, slowly, gently, in just a little while. That elder, by the way, had a name, Philipp von Jolly, a physicist in Munich, well-respected, kind enough to take a promising student aside and offer him a little honest advice. And the advice was this: don't go into physics. The great work is done. The grand cathedral is built, and all that remains is a bit of dusting, a few small measurements to tidy up the corners. A young man with ambition, he seemed to be saying, would be wasting himself here. It's a lovely thing to picture, isn't it? The two of them standing there, the older man gesturing at a finished world, the younger one listening politely. Neither of them knowing that the boy in front of him would, within a single lifetime, take that finished cathedral apart stone by stone. Not out of rebellion, not out of any hunger to overturn anything, but almost by accident, while trying his hardest to keep it standing. So let me introduce him to you properly now that you've met the moment that shaped him. Max Carl Ernst Ludwig Planck, born on the 23rd of April 1858 in the northern German port city of Kiel. And if you wanted to design a person least likely to start a revolution, you might end up with someone very much like him. He was devout, he was formal, he was, by every account, a deeply conservative man, and I don't mean that in any political sense. I mean it in his bones, in the way he saw the world. He revered order, he revered permanence, he believed, with something close to religious feeling, in the eternal absolutes of nature. The idea that there were laws underneath everything, fixed and beautiful and unchanging, laws that had always been true and always would be. That was what drew him to physics in the first place, not the thrill of the new, the comfort of the forever. And so think about what he actually said to von Jolly that day in Munich. The older man told him there was nothing left to discover, and Planck, far from being discouraged, was almost reassured by it, because, he answered, he had no wish to discover new things. He only wished to understand the fundamentals that were already known, to grasp the eternal truths more deeply, to live inside the finished cathedral and learn every inch of it by heart. Sit with that for a second, here in the quiet, because it's the whole story, folded up small. The man who would one day crack the foundations of physics open chose the field precisely because he thought it could never be cracked. He went looking for the unshakable, and the unshakable is exactly what he ended up shaking. He played the piano beautifully, by the way. He was the kind of man who loved Bach and Brahms, who found in music the same thing he found in physics, that sense of an underlying harmony, a structure you could trust. A formal, gentle, somewhat old-fashioned soul, even by the standards of his own time. Not a firebrand, not a rebel scribbling manifestos in the margins, a traditionalist who wanted, more than anything, for the great truths to stay great and true. Keep that picture of him close, because everything that follows only lands if you hold on to it. The deeper his love of certainty, the harder the irony falls. This isn't the story of a bold young radical storming the gates. It's the story of the gatekeeper himself, the one who loved the gate most, being forced, against everything he believed, to open it. And here is the thing I most want you to carry into the dark with you tonight. Years later, an old man by then, Planck, would write a letter. 18 years into the new century, more than 30 years after that conversation in Munich. He wrote it to a physicist named Robert Williams Wood in 1931. And in that letter, looking back across his whole life at the single thing he was most famous for, the discovery that had made him immortal, he did not call it a triumph. He did not call it brilliant or inevitable or even a discovery at all. He called it an act of desperation. Let those words settle over you for a moment. An act of desperation. This is the man whose name now sits at the very foundation of modern physics. A man whose work split the calm, continuous world of the old science clean in two. And when he reached for words to describe what he'd done, the word he chose was desperation. He wrote that he had been ready in that moment to sacrifice any of his previous convictions, every belief he held, because, as he put it, a theoretical explanation simply had to be found at any price, however high. At any price. That's a strange thing to say about a moment of genius, isn't it? It's the language of a man cornered, a man who had run out of every other option and was reaching, almost in despair, for the one move he'd sworn he would never make. We're going to find out slowly, over all the time we have together tonight, exactly what cornered him. What problem could possibly push a careful, conservative, order-loving man into something he'd describe as desperation for the rest of his days? What he was so frightened of giving up, and what, in the end, he gave up anyway. But not yet, for now it's enough to hold the shape of him in your mind. The boy in Munich, told the work was finished, the man who only ever wanted to understand, and the equation still waiting somewhere up ahead, in the dark, that he would write down with his own hand, and then spend more than a decade trying and failing to unwrite. So let us begin with a problem, a very specific, very stubborn problem, one that had been sitting at the edge of physics like a splinter in the thumb, not disabling, not catastrophic, but persistently, irritatingly there, for the better part of a decade before Planck finally sat down and really looked at it. The problem was light. Not light in some grand philosophical sense, but light behaving in a way that nobody could fully explain. And the place to begin understanding it is with an object that does not really exist, at least not in the perfect form that physicists imagined it. They called it a black body. You can think of a black body this way. Take any ordinary object, a coffee cup, a brick, a stone picked up from a garden path. Real objects are complicated things. They absorb some of the light that hits them, but they also reflect some back, and they do so in ways that depend on their color, their texture, their chemical composition, all kinds of messy, specific details. A red mug absorbs certain wavelengths of light and bounces others back toward your eye, and that bouncing back is precisely what makes it look red. A black object, an object that we call black in everyday life, absorbs most of what hits it, but still not all. Nothing in the real world is quite perfect. The black body physicists had in mind was an idealization, a hypothetical object that absorbs absolutely everything, every wavelength, every frequency, every scrap of radiation that lands on it. Not almost everything, everything. And because it absorbs everything without preference, it also re-emits radiation without any of those messy individual preferences. When you heat it up, the radiation it gives off depends on one thing and one thing only: its temperature. Not its color, not its material, just the temperature. You might be wondering why anyone would care about a made-up perfect object when real physics happens in the real world with real, imperfect things. And the answer, as is so often true in physics, is that the idealization turns out to be deeply, surprisingly useful. Because once you know how a perfect emitter and absorber behaves, you have a baseline, a standard, against which you can measure everything else. Real objects deviate from the ideal, but understanding the ideal first gives you the map. And here is where the story begins to get interesting, because physicists in the late 19th century had not just thought about the black body in the abstract, they had actually built one, or something very close to it. If you take a hollow metal box, imagine an oven, sealed shut except for a very small hole, and you heat that box to some known temperature, then the tiny amount of light that leaks out of the hole is almost a perfect sample of black body radiation. The hole itself behaves like a black body. Any light that enters through the hole bounces around inside the cavity, being absorbed and re-emitted by the walls again and again until it has reached thermal equilibrium with those walls. And the little that escapes out the hole carries the signature of the temperature and nothing else. This is the kind of object physicists could actually study. A heated cavity with a small opening leaking its quiet glow into a detector. And what they were trying to do was map that glow. Measure precisely how much energy was being emitted at each different wavelength, at each different temperature, and then find the mathematical law that described the pattern. It sounds, when you say it that way, like a tidy, manageable project. It was not. Now there is another layer to this story that most accounts leave out or mention only in passing, and I find it one of the most quietly charming details in the whole affair. The people doing this work, the experimentalists making those careful, precise measurements of blackbody radiation in Berlin in the 1890s, were not doing it, at least not entirely, for the sake of pure science. They were doing it because someone needed to know how bright a light bulb was. The late 19th century was the age of electrical light. Gas lamps were giving way to carbon filament bulbs, which were giving way in turn to newer and better designs, and manufacturers needed a standard, a reliable, internationally agreed upon way to rate how efficiently a lamp converted electrical energy into visible light. The German government, which took industrial and scientific precision seriously in a way that was almost constitutional, had set up an institution specifically for this kind of work, the Physikalisch-Technische Reichsanstalt, the Imperial Institute of Physics and Technology in Berlin. You can call it the PTR, which is easier to carry through a long night. The PTR was housed in a handsome set of buildings in the Charlottenburg district, and among its responsibilities was the development of radiation standards, precise measurements of how much light and what kind of light a heated object at a known temperature would emit. Because a glowing lamp filament is, to a reasonably good approximation, a black body. If you understood the black-body radiation law exactly, you could use that understanding to design and certify lamps with confidence. The quantum was born in part because someone in Berlin wanted to know how to rate a light bulb accurately. That's the kind of detail history tends to smooth over. We like our great revolutions to begin with grand, abstract questions. And sometimes they do, but sometimes they begin with someone needing a better way to measure the brightness of electric lighting, and the physics follows on behind. The experimentalists who did this work deserve names because they were serious and careful scientists who produced results of real precision. There was Otto Lummer, one of the leading experts in the optics of radiation. There was Ernst Pringsheim, who worked closely with Lummer on the measurements. There was Ferdinand Kurlbaum, another PTR physicist, making systematic measurements of spectral intensity. And there was Heinrich Rubens, who had developed exceptional skill in measuring the long wavelength end of the spectrum, the far infrared region where light waves are too slow and too long to see. Waves you feel as warmth rather than see as color. Through the second half of the 1890s, these four men built increasingly precise experimental setups, heated their cavity ovens to known temperatures, and measured with care how much radiation emerged at each wavelength. They weren't guessing, they were mapping, and the map they produced was accurate and detailed and beautifully consistent, and it had exactly one problem. Nobody could derive it from theory. The existing laws of physics could not explain the shape of the curve they were measuring. Now let me try to give you a picture of that curve, because it is a lovely thing, and understanding its shape is the first step toward understanding why it was such trouble. If you were to draw a graph, and you don't need to follow the precise mathematics to get this, so settle in, you might put wavelength along the bottom axis, and the amount of energy being emitted at each wavelength up the vertical axis. At very long wavelengths, the black body emits relatively little energy. As the wavelength shortens, as you move from infrared toward visible light and then toward ultraviolet, the energy rises, reaching a peak, and then it falls again as the wavelength gets shorter still. The curve has a hump in it, a rise, a peak, a fall. And as you heat the object hotter, the whole curve shifts, more total energy, and the peak moves toward shorter wavelengths. This is why hot things glow red first, then orange, then white. The peak is moving, carrying the brightest emission toward the visible and bluid as temperature rises. That much the experimentalists had measured beautifully. The question was, what law, what formula, what derivation from first principles could reproduce this curve exactly across all wavelengths and all temperatures? Two theoretical answers were on the table by the end of the 1890s, and together they form one of the most instructive failures in the history of science. The first came from Wilhelm Wien. Wien was a German physicist who had already made important contributions to understanding how the peak of the blackbody curve shifts with temperature. The relationship now called Wien's displacement law, published in 1893. In 1896 he went further and proposed a formula for the full shape of the radiation curve. And Wien's formula worked beautifully. At short wavelengths and high frequencies, at the blue and ultraviolet end of the spectrum, the curve it predicted matched the measurements almost perfectly. For years, Wien's formula was the accepted answer. But Lummer and Pringsheim, making more careful measurements at longer wavelengths, began to notice that something was off. At the red and infrared end of the spectrum, Wien's law predicted values slightly too low. The discrepancy grew larger as the wavelength grew longer. At the far infrared end, where Rubens had developed his finest measurements, the law failed clearly and unmistakably. Wien's formula was not the complete answer. It was a half answer. It worked in one region and broke in another. This was the state of affairs in the autumn of 1900. The second theoretical approach came from an entirely different direction, and it was, in a sense, purer. It was built not on Planck's kind of thermodynamic reasoning, but on the solid bedrock of classical physics' most successful general principle. Lord Rayleigh, John William Strutt, 3rd Baron Rayleigh, a British physicist of considerable distinction, published a theoretical treatment in 1900 based on what was called the equipartition theorem. The idea behind equipartition is intuitively appealing, and I will try to give you the shape of it without the mathematics. Imagine the inside of that heated cavity, the black-body oven, as being filled with standing waves of electromagnetic radiation. Waves bouncing back and forth between the walls, a continuous babble of oscillations at every possible frequency. The equipartition theorem, which sits at the heart of classical statistical mechanics, says that in a system in thermal equilibrium, each available mode, each distinct way that energy can be stored, should on average receive the same amount of energy. Not more, not less. The same share fairly distributed for every mode. This sounds entirely reasonable. It is, in fact, one of those principles that feels almost self-evident once you hear it. If energy is sloshing around in a system that has reached equilibrium, why should any one mode get more than any other? Of course, they should share equally. That is what equilibrium means. The problem, the catastrophic total physics shattering problem, is that there are not finitely many modes. As you go to shorter and shorter wavelengths, as you go to higher and higher frequencies, there are more and more possible standing waves that fit inside the cavity. In fact, the number of modes grows without bound as the wavelength shrinks. If each mode gets the same share of energy and the number of modes keeps growing toward infinity at short wavelengths, then the total energy radiated at short wavelengths should also grow toward infinity. Let me say that another way because it is so striking that it deserves a second pass. Classical physics, the physics of Newton and Maxwell and all the giants who built the edifice of 19th century science, predicted, in black and white, with impeccable logic, that every warm object should emit infinite energy at short wavelengths. Specifically, as you push toward ultraviolet light and beyond, the predicted energy should climb without limit and never stop. Your kettle sitting on the stove, your coffee cup, a candle flame, a warm living body, your own body, lying in bed right now. Classical physics insisted that each of these should be blazing with essentially infinite amounts of ultraviolet radiation and beyond. They should not merely glow warm, they should each be pouring out energy so freely and so completely across all short wavelengths that they would, by rights, illuminate and incinerate everything around them. The universe should be a seething inferno of radiation from every warm thing in it. You should not exist. The cosmos should have been catastrophically full of radiation from the first moment there was anything warm enough to emit it. And of course, this does not happen. You are lying in bed reading or listening, not being incinerated. The kettle boils without blazing ultraviolet. The candle glows softly, warmly, in its small domestic way. Reality refuses to behave according to the formula. The name most commonly attached to this prediction, the one you may have encountered before, is the ultraviolet catastrophe. And here is one of those small but pleasing precision points that the careful historian of science enjoys noting. The phrase itself was not invented in 1900. It was coined in 1911 by the Austrian physicist Paul Ehrenfest, who used it retroactively to name the failure that had already, by then, been solved. So if you picture the Berlin physics community in the autumn of 1900 huddled together discussing the ultraviolet catastrophe by name, That is a small historical anachronism, a good name applied to a real disaster a decade after the disaster had been patched over. The catastrophe was real, the catchy name came later. Lord Rayleigh's approach, later refined and published in 1905 by Sir James Jeans, a British physicist who completed the derivation rigorously, gave what became known as the Rayleigh-Jeans law. And it had precisely the opposite failure to Wien's law. Where Wien's formula worked at short wavelengths but failed at long ones, the Rayleigh-Jeans formula worked beautifully at long wavelengths. At the infrared end, it matched the experimental data quite well, but diverged catastrophically at short ones. It correctly captured one end of the curve and destroyed the other. Two formulas, each fitting half the curve, each failing exactly where the other succeeded, neither one capable of capturing the whole thing. This is the moment to pause and appreciate the strangeness of the situation that Planck and his colleagues found themselves in. They were not in 1900 looking at vague discrepancies or minor anomalies. The failure of classical theory to account for the short wavelength behavior of blackbody radiation was not a rounding error. It was an absolute, fundamental breakdown. The most carefully constructed and universally trusted framework in all of science, a framework that had conquered mechanics, optics, electromagnetism, thermodynamics, that had predicted the speed of light and the behavior of gases and the orbits of planets, was producing, when applied to this one quiet, specific problem of a heated cavity and its glow, a result so absurd as to be physically impossible. Every warm thing in the universe radiates infinite energy. That is what the best available classical theory said. And every warm thing in the universe in practice does not. Something was wrong. Something at the level of foundations, not details. Now Planck knew all of this. He had been following the experimental results from the PTR closely, and he had been working on his own theoretical approach to the radiation problem for several years. His angle was different from Rayleigh's. He was approaching it through thermodynamics and the concept of entropy rather than through the equipartition theorem, but he was wrestling with the same fundamental difficulty. And it was here, in the warm autumn of 1900, that the story takes a turn that belongs properly in the next chapter of our journey tonight. But before we get there, stay with me for a moment in this picture that the classical world had built. The world of Lord Rayleigh and James Jeans and Wilhelm Wien, the world of smooth, continuous energy flowing without limit, the world in which a heated object simply poured its energy out along an infinite spectrum in a perfect democratic sharing among all possible frequencies. There was something beautiful about that picture in a way, something geometrically clean about equipartition, about the idea that energy spreads itself evenly, that no frequency is favored over any other. It was orderly, it was logical, it followed from first principles with mathematical rigor. It just happened to predict that you should not exist. That is the strange and slightly vertiginous position that classical physics found itself in at the threshold of the 20th century. Not unsure, not merely incomplete, but producing from its best and most carefully constructed tools a prediction that was not slightly wrong, not approximately wrong, but infinitely, catastrophically, impossibly wrong. Not a hairline crack in the edifice, a hole straight through the foundation. And Planck, remember who Planck is, the careful, classical conservative, the man who had been told physics was finished and had decided he was content to understand what was already known. Planck was staring at this hole. He had been staring at it for the better part of a decade. He was not a revolutionary. He did not want to blow anything up. He wanted the framework to hold. He had invested his deepest professional self, his philosophical conviction, in the belief that the great laws of thermodynamics were not just practically useful, but absolutely, eternally true. And here was a simple, practical problem about a heated cavity and a glow of light, and the existing laws could not touch it cleanly. Something had to give. The measurements kept coming. Otto Lummer and Ernst Pringsheim refining the short to middle wavelength range, Ferdinand Kurlbaum working on the absolute values, and Heinrich Rubens, meticulous, patient Heinrich Rubens, probing the far infrared end of the spectrum where the long waves lived, where Wien's law had begun to quietly fail. Think for a moment about what these men were doing in their Berlin laboratory. It is easy, at this distance, to think of experimental physics in the abstract. Curves on paper, numbers in a table. But the work was material and physical and slow. The cavity ovens had to be built and calibrated, heated to exact temperatures and held there steadily. The detectors had to be precise enough to register the tiny differences in intensity between one wavelength and the next. The measurements had to be taken at enough different temperatures and wavelengths to trace the full shape of the curve with confidence. This was painstaking, repetitive, careful work, done over years, and when Rubens and his colleagues looked at what they had was good, better than good, precise enough to be trusted, systematic enough to show a clear pattern, consistent enough that no amount of wishful thinking could explain away the discrepancy with the theoretical formulas. Wien's law failed in the infrared. The failure was real. The numbers showed it. And it was these numbers, specifically the far infrared results, the measurements at long wavelengths, that Rubens brought to Planck one day in early October of 1900. A Sunday, as it happens. Rubens came to Planck's house because scientists in Berlin at the turn of the century were the kind of colleagues who visited each other's homes, who talked about physics over a meal and went home afterward to keep thinking. Rubens arrived with data. The two men discussed what it meant. And by the time Rubens left, the shape of the problem had clarified for Planck in a way it had not been clear before. The long wavelength data was not just a gentle nudge away from Wien's law. It was a clean, decisive discrepancy, and when you looked at that data alongside what Wien's formula predicted, and alongside the Rayleigh-type approach and what it predicted, you could see, if you were Planck, if you had been thinking about entropy and radiation for years, that there was a pattern. Wien's law and the Rayleigh approach each captured one half of reality. The correct formula, whatever it was, had to smoothly connect both halves. It had to reduce to Wien's result at short wavelengths and high frequencies, and it had to behave in the way Rubens' long wavelength data showed at the other end. Planck went home that evening, or possibly stayed in that evening, the account is not precise enough to say with certainty, and he began to think about interpolation. Not from physical principles, not from some deep insight into the mechanism of radiation, but from the mathematics of the problem. If you know what the answer must look like at the two extreme ends of the spectrum, and you have good data filling in the middle, you can sometimes guess the right formula by looking for the simplest mathematical expression that smoothly bridges the two ends. This is exactly what Planck did. He was not, in that initial step, deriving anything from physical theory. He was curve matching, looking for a formula that fit. And within a remarkably short time, within what seems to have been a matter of days, he found it. An elegant interpolation between Wien's formula and the Rayleigh-type result, a single mathematical expression that when you checked it against all the available experimental data, fit beautifully. Short wavelengths, long wavelengths, everything in between across a range of temperatures. On October 19, 1900, Planck presented this formula to the German Physical Society at a meeting in Berlin. He had the equation. It worked. He could not yet explain why it worked because he had not derived it from any physical principle. He had guessed it in the most educated and mathematically informed sense of the word guess. And the guess was right. But a correct formula pulled out of the air without a physical justification is not physics, it is curve fitting, and Planck knew this. Rubens, that same evening or shortly after, went home and checked Planck's new formula against his own far infrared measurements. And when he came in the next morning or sent word, he confirmed the new formula fit perfectly across the whole wavelength range. This was not Wien's law failing at long wavelengths. This was a new formula that agreed with everything. Good. But Planck had a problem. He still had no idea why it worked, and this, the gap between having the right answer and understanding why it was the right answer, was the thing that would push him toward what he would later call his act of desperation. Because a physicist of Planck's temperament could not rest with a formula that fit but lacked a foundation. The formula was a coincidence until it was explained, and to explain it he would have to go much deeper. He would have to confront not just the mathematics but the physics, and the physics, when he finally looked at it clearly, was going to force him somewhere he very much did not want to go. The curve of black-body radiation had been measured. The catastrophe of the classical prediction had been documented, even if its name had not yet been coined. Two laws, Wien's from one end, Rayleigh's from the other, had each shown what they could and could not do, and the shape of what was needed had been glimpsed. What was missing was the reason, the physical mechanism, the answer to the question, why does radiation actually behave this way? What is happening inside the walls of that heated cavity at the level of matter and energy that produces a curve with a peak, a hump, a rise and fall, rather than the climbing forever infinite disaster that classical theory demanded? That answer would come, as answers often do, in a way its author did not expect and would not entirely welcome. But let us not rush there yet. Let us sit for a moment with the problem as it stood in October of 1900. Planck had a formula, a good one, a correct one, as far as the experimentalists could tell. He had presented it to his colleagues, who had noted it and moved on. Because a formula without a derivation is a suggestion, not a proof. And suggesting a formula is not the same thing as understanding why nature behaves as it does. He had weeks, not months, before the next meeting of the German Physical Society. And he had a derivation to construct. Here is what he knew he had to work with. The cavity walls, the walls of that black body oven, which were made of matter, of atoms and molecules. And those atoms and molecules could oscillate, vibrate, wiggle, just as any physical thing can vibrate when it has energy. These oscillators in the wall were the things that absorbed the radiation coming in and emitted radiation going out, and the balance between absorption and emission was what determined the spectrum, the distribution of energy across different frequencies, that the cavity radiated in thermal equilibrium. This much was not controversial. Planck had been thinking about these oscillators for years, and his thermodynamic approach had always centered on them. The question was, what exactly is the relationship between the energy stored in an oscillator at a given frequency and the radiation that oscillator produces? In classical physics, the answer was clear, and it was built on the equipartition theorem, the same equipartition theorem that led Lord Rayleigh to his catastrophically wrong prediction. Each oscillator at each frequency, according to classical theory, should have an average energy that depended only on temperature and not on frequency, equal energy for all frequencies at all times, and that equal sharing was the seed of the catastrophe. Because if each frequency's oscillators carry the same energy, and there are infinitely many frequencies available at short wavelengths, the total energy radiated becomes infinite. Planck needed a derivation of his new formula that avoided this conclusion, and he found one, but in finding it he was forced to do something that violated one of the deepest assumptions in classical physics, an assumption so basic so intuitively obvious, so thoroughly woven into every calculation anyone had ever done, that most physicists would not have thought to call it an assumption at all. It was just reality. It was just the way the world worked. The assumption was continuity, the idea that energy is continuous, i.e. that it can take any value, that you can have any amount of it, that it flows and accumulates smoothly and without gaps. This is how water works. This is how heat works. This is how electricity works in the way it feels and behaves at human scales. You can warm a cup of tea by any amount you like, not just by 1 degree or 2 degrees, but by any fraction of a degree, continuously, smoothly, without any step or jump. Energy in classical physics was a smooth substance, divisible without limit, flowing without graininess. To derive his formula from first principles, Planck was forced to abandon this. He was forced to assume that the oscillators in the cavity wall could not have just any amount of energy. They could only have energy in multiples of a specific, fixed amount, a minimum chunk, a smallest possible unit, that depended on the frequency of the oscillator. The higher the frequency, the larger the minimum chunk. An oscillator vibrating at twice the frequency could only gain or lose twice as much energy per transaction. If you have been keeping half an eye on your pillow and half on what I am saying, this might be the moment to let it sink in gently without grasping too hard. The picture is this. Imagine you are filling a container with water, but the water only comes in fixed bottles. You cannot add a trickle. You cannot add a cup. You can only add 1 bottle, or 2 bottles, or 3 bottles, never half a bottle, never a quarter. The water comes in discrete units, and no finer division is possible. Now imagine that the size of the bottle depends on the frequency you are working with. For high frequencies, the bottle is large. For low frequencies, the bottle is small, but it is never infinitely small. There is always a minimum. This is what Planck was proposing mathematically for the energy of his oscillators, not water, obviously. Energy. But the principle is the same. Each oscillator could hold energy only in whole multiples of a smallest possible amount. That amount, that irreducible energy unit, he called the energy element, and he denoted it by the Greek letter epsilon. And the size of this element was proportional to the frequency of the oscillator. Epsilon equals h times nu, equipartition, where nu is the frequency and h is a new tiny constant that Planck introduced to make the formula work, Planck's constant. That is what h would come to be called. He himself did not initially know what to call it or what it meant. It was a number. It's a very small number, approximately 6. 626 times 10 to the power of negative 34 in units of joule seconds, that Planck calculated by fitting his formula to the experimental data. And when he calculated it, he found that his value was remarkably close to what we now know to be the correct value. His guess at h in 1900 was good, astonishingly good. The smallness of h is worth dwelling on because it explains something important. 6.626 times 10 to the power of negative 34 joule seconds. That means the decimal point followed by 33 zeros, followed by the digits 6626. It is an almost incomprehensibly tiny number. And this tininess is precisely why the quantum graininess of energy is invisible in everyday life. The minimum energy chunk for any oscillator at ordinary frequencies, at the frequencies of sound and light and heat that we encounter in our daily experience, is so vanishingly small compared to the total energies we work with that the graininess is completely invisible. Energy looks smooth and continuous in ordinary life because the steps are so small that no measuring instrument in the human world can detect them. The grain of reality is finer than anything we normally see or feel. But at the level of individual atoms and molecules vibrating at very high frequencies, the chunks are not nothing. They are small, but they are real and they matter. And it is at those scales, in those high-frequency oscillators, that the quantum graininess makes all the difference between the classical catastrophe and the real behavior of black body radiation. Here is how it matters, and this is the gentle heart of the explanation, so let it land at whatever pace feels comfortable. In classical physics, every oscillator at every frequency gets the same average energy regardless of frequency. That is the equal sharing principle, the equipartition theorem. There is no mechanism to suppress the high-frequency modes. They get their equal share just like the low-frequency modes do. And because there are infinitely many of them, the total blows up. But in Planck's picture, the high-frequency oscillators have a problem. Their minimum energy chunk, their E-Chen, is large. It is large because frequency is large and the chunk grows with frequency. To have any energy at all in a high-frequency oscillator, you have to be able to afford at least one full chunk. And the thermal energy available in the system, with the energy associated with a given temperature, is finite. At a given temperature, the thermal energy sloshing around is a definite finite amount. If the minimum chunk for a very high-frequency oscillator costs more energy than the thermal bath can afford, then that oscillator simply does not get excited. It stays dark, it stays at zero, not almost zero, at exactly zero, because you cannot have half a chunk. You cannot have a fraction of a minimum unit. You either have one or you have none. And so the high-frequency modes, the ultraviolet modes and the modes beyond, are frozen out. The thermal bath cannot afford their minimum energy requirement, and so they take nothing. They do not participate. And because the highest frequency modes take nothing, the total energy radiated at short wavelengths does not go to infinity. It drops off, gently and precisely, in the shape that Lummer and Pringsheim and Rubens had measured so carefully. The hump, the peak, the fall. The catastrophe is averted, not by any force or any field, but simply by the arithmetic of discrete chunks and a finite energy budget. This was the physics behind the formula. This was what the derivation said. But to get to this derivation, Planck had needed one more ingredient, and this ingredient was perhaps the most painful of all for a man of his philosophical commitments. He had needed to use a mathematical technique developed by Ludwig Boltzmann. Boltzmann was an Austrian physicist, a man of enormous intellectual energy and deep originality, and he had spent decades developing what we now call statistical mechanics, a framework for understanding the thermodynamic properties of matter, not by treating matter as a smooth, continuous fluid, but by counting the possible arrangements of its discrete parts and asking how energy is statistically distributed among them. Statistical mechanics is, at its heart, a counting game. You divide energy into small elements, you count the number of ways those elements can be distributed among the particles or oscillators in the system, and you find the distribution that has the most possible arrangements, because that is overwhelmingly the most probable state. Boltzmann's approach was brilliant and it worked, but it came with a philosophical price. Because statistical mechanics, by its very nature, makes the second law of thermodynamics, the law that heat flows from hot to cold, that entropy tends to increase, that the universe tends toward disorder. Not an absolute, eternal truth, but a statistical one. A probabilistic one, overwhelmingly likely, yes, universally true in practice, essentially, but not at the deep level of mechanics, absolutely guaranteed. In principle, in a statistical framework, there is an astronomically tiny probability that heat could flow from cold to hot. Not because the laws allow it on purpose, but because the random motions of particles could, by pure chance, happen to arrange themselves that way. Planck hated this. Or rather, Planck had spent a significant portion of his career arguing against it. He believed the second law was absolute and non-statistical. He believed in eternal, deterministic, physical law that held not because of probabilistic counting, but because of deep, fundamental necessity. He and Boltzmann had been, in the most polite sense, philosophical opponents, not enemies. Physics at this level was conducted with civility, but occupying genuinely contrary positions on a question that both men cared deeply about. And now, in December of 1900, trying to construct a derivation of his formula from first principles, Planck found that the only way to make it work was to use Boltzmann's method, the statistical counting approach, dividing the energy into discrete elements, counting the arrangements, finding the most probable distribution. He used the very tool he had resisted. He held his nose, philosophically speaking, and did the counting. And when he did, the formula came out. The correct formula, the one that matched all the data, emerged naturally and cleanly from the calculation, but only because the energy elements were finite and discrete and proportional to frequency. The discreteness was not an assumption he could relax afterward. It was not a mathematical convenience that could be smoothed away once the calculation was done. It was load-bearing. If you let the energy elements shrink towards zero, if you took the limit as the chunk size went to nothing and energy became continuous again, the formula collapsed back into the Rayleigh-Jeans catastrophe. The discreteness had to be real, or the derivation failed. On December 14, 1900, Planck presented this derivation to the German Physical Society. This date is the one that physicists would later call the birthday of quantum theory. He presented the mathematics, he showed the derivation, he exhibited the formula, and he introduced formally and in print the constant h and the energy element A cam. What he did not do on December 14, 1900, and this is the thing that the conventional story so often misses, was claim to be announcing a revolution. He did not stand before his colleagues and say, "Gentlemen, I have broken classical physics. The era of continuous energy is over. The quantum age has begun." He did nothing of the sort. What he did in the days and weeks and years that followed was try to figure out how to make his own result go away. But that, the decade of trying to undiscover the quantum and all the people who took it further than Planck ever dared, that belongs to the next part of tonight's journey. For now, rest here with the shape of what has been built. A black body, that idealized, perfectly absorbing object, manufactured in practice from a heated cavity in a Berlin laboratory by Lummer and Pringsheim and Kurlbaum and Rubens, men with precision instruments and long winters and a problem that would not resolve. The classical prediction that infinite energy should blaze from every warm thing, a prediction not named for another 11 years, when Paul Ehrenfest would give it the retroactive label we carry today. Two half formulas, each capturing what the other could not. Wien's law at short wavelengths and the Rayleigh-Jeans approach at long ones, meeting in the middle only in failure. And then Planck, the careful conservative with his thermodynamic instincts and his philosophical preferences, sitting down with Rubens's data in an October of the last year of the old century, and finding, by interpolation first, by derivation second, the formula that fit everything. A formula that required a constant h with 33 zeros in its decimal expansion, a formula that required energy to come in chunks, a formula that worked perfectly and that Planck already knew on some level had cost him something irreplaceable. The equation was written, the constant was defined, the curve was explained, and the man who had written it all down was already, quietly, beginning to wonder if there was any way at all, to take it back. And so we arrive at the moment the equation entered the world. Not with a thunderclap, but with a pen and a problem, and a man working at his desk in the particular quiet of October 1900, somewhere between desperation and precision, trying to reconcile numbers that refused to be reconciled any other way, but to understand what Planck did and why it cost him so much. We need to spend a few more minutes with the failure that preceded him. The failure that was not his, but that became his problem to solve. Lord Rayleigh had made his attempt in the same year, 1900. John William Strutt, 3rd Baron Rayleigh, was one of England's finest theoretical physicists, methodical, rigorous, a man who had spent decades thinking carefully about waves and vibrations and the behavior of light. He came at the black-body problem from the direction that classical physics most naturally suggested, the equipartition of energy. This is one of those ideas that sounds entirely reasonable when you first encounter it, and that is precisely why it went so catastrophically wrong. The idea is this: when you have a system in thermal equilibrium, a hot gas, a cavity full of radiation, any system where energy is sloshing around freely, that energy tends over time to distribute itself equally among all the available modes. Each mode, each possible way the system can vibrate or move or oscillate, gets an equal share of the total energy. Equipartition. It is, in many ways, a beautifully democratic principle. Energy as something that spreads itself fairly. Think of it this way: imagine you have a room, and in that room you can play music at various frequencies. A low note here, a middle note there, a high note somewhere else. In the classical picture, energy doesn't particularly care which frequency it occupies. It distributes itself across all of them, giving each one the same amount. And here is where the trouble begins. Because in a cavity of radiation, the number of available modes, the number of different frequencies at which the walls can vibrate and emit light, increases very steeply as you move toward shorter wavelengths. Higher and higher frequencies, more and more possible modes, and each one demanding its equal share. If energy truly distributes equally across all modes, and if the number of modes grows without bound as wavelengths get shorter, then the total energy of the radiation goes up without bound too. You keep adding more modes, each demanding its portion, and the sum never closes. The prediction, worked out carefully from the classical principles, is that a black body in thermal equilibrium should pour infinite energy into the short wavelength end of the spectrum. Infinite. Not a large number, infinity itself. Rayleigh saw this. He wrote about it, somewhat carefully hedging his result, in 1900. James Jeans, a younger theoretical physicist who would refine and complete the calculation in 1905, would later confirm the same result more rigorously. Between them, Rayleigh and Jeans produced what we now call the Rayleigh-Jeans law, a formula that describes how much energy a black body radiates at each wavelength, derived cleanly and correctly from classical equipartition. At long wavelengths at the cool, gentle infrared end of the spectrum, it works. The numbers match what the PTR experimenters measured. Rubens and Kurlbaum and Lummer and Pringsheim, with their meticulous instruments and their long series of measurements in the late 1890s, confirmed it in that range. So Rayleigh was not simply wrong, he was right where the classical tools were appropriate. The formula fits beautifully as wavelengths grow longer and frequencies drop lower. But move toward shorter wavelengths, toward blue light, toward violet, toward the ultraviolet, and the Rayleigh-Jeans law begins to climb, and keep climbing, reaching upward without any mechanism to stop it, predicting energy densities that spiral toward infinity. This is the catastrophe, not that the formula fails to fit the data in some minor way, it fails to remain finite. It predicts a physical quantity, energy, becoming arbitrarily infinitely large, which is not a minor discrepancy but a fundamental breakdown of the mathematical machinery. Paul Ehrenfest would coin the term ultraviolet catastrophe in 1911, giving it the name by which we remember it now. But in 1900, the disaster didn't have a dramatic label. It was simply the fact that classical physics, taken seriously and honestly at short wavelengths, said something that was plainly, obviously not true. That every warm object in the universe should be radiating infinite energy and incinerating everything around it. Your stove. A a glowing coal, a candle flame, your own living body warm at 37 degrees. According to the Rayleigh-Jeans law, each of these should be blazing uncontrollably into the ultraviolet and beyond, pouring out energy without limit. And yet nothing of the sort was happening. Candles were not incinerating rooms. Human bodies were radiating warmth in a perfectly ordinary and finite way. The discrepancy between what classical theory demanded and what reality quietly provided was not a rounding error. It was an absurdity. So there it stood, Wien's law working at short wavelengths, failing at long ones. Rayleigh's classical result working at long wavelengths, catastrophically failing at short ones. Two half answers, each covering the other's failure, meeting only in contradiction. The blackbody spectrum, that smooth, bell-shaped curve that the PTR experimenters had measured so precisely, sat calmly in the middle of both failures, conforming to neither one across its full range. Something had to bridge them. No one knew what. And then, on or around October 7, 1900, Heinrich Rubens came to visit Max Planck at his home in Berlin. Rubens was one of the PTR experimentalists, careful, precise, the man responsible for some of the most accurate far-infrared measurements anyone had yet made. He had data, fresh data from the long wavelength end of the spectrum, the far-infrared region where Wien's law was visibly failing, and where the numbers were behaving in a particular, revealing way. He brought these measurements to Planck, perhaps over coffee, perhaps at the dinner table, in one of those unremarkable domestic settings where the history of science sometimes quietly pivots, and shared what he had found. The long wavelength data confirmed something specific. In that region, the energy density of the blackbody radiation was increasing in a particular clean way, proportional to the temperature, simply and linearly. Not the exponential fall-off that Wien's formula predicted, something simpler, something more gentle. Planck took this in. He had been thinking about the blackbody problem for years, approaching it from his characteristic angle: thermodynamics, entropy, the second law, the behavior of oscillators in the cavity walls. He had his own earlier attempt at a radiation formula published in 1899 which had matched Wien's law closely. He knew its shape, he knew where it failed, and now Rubens was showing him with measurements in hand exactly what the failing end of the spectrum actually looked like. That evening, Planck sat down and tried to find a formula that worked across the whole range. What he did, and it is worth sitting with how honest he was about this in retrospect, was interpolate. He had Wien's formula on one side, working at short wavelengths. He had the new data on the other side, showing what the long wavelength behavior actually was, and he searched mathematically for the simplest possible expression that would smoothly connect the two, that would reduce to Wien's law at one extreme and match the Rayleigh-type behavior at the other. This is not physics from first principles, this is curve fitting, educated, mathematically sophisticated curve fitting, but curve fitting nonetheless. He was not deriving the answer from a deep theory, he was finding the equation that the data seemed to demand and hoping that the underlying physics would explain itself afterward. He found it that evening or shortly after. A formula of a particular mathematical form involving two constants which we now call h and k, Planck's constant and Boltzmann's constant. When he tested it against Rubens's data, it fit. At short wavelengths, it reproduced Wien's law. At long wavelengths, it matched the new infrared measurements. Across the whole spectrum, the smooth bell-shaped curve that the PTR experimenters had so carefully mapped, it fit exactly without residual. He sent the formula to Rubens that same night, in a postcard. Rubens checked it against his data in the morning. It matched. On October 19, 1900, less than 2 weeks after that visit, Planck presented the formula to the German Physical Society in Berlin. He had a formula, a result, a curve that fit the data better than anything else on the table. The October 19th presentation was the empirical announcement. Here is an equation that describes what the experiments show. But Planck knew with the intellectual honesty that was one of his most characteristic qualities that this was not enough. A formula that fits the data without a derivation, without a physical reason why it should be true, is incomplete. It is a description, not an explanation. Physics for Planck meant understanding why. The formula was written, but the justification had not yet been found. He went back to work. The weeks that followed, the weeks between October 19th and December 14th, 1900, were by Planck's own account among the most intense of his scientific life. He had a formula. He needed a theory. And to find it, he was going to have to do something that philosophically cost him a great deal. He was going to have to use Ludwig Boltzmann's method. This matters more than it might seem at first, because to understand what Planck sacrificed in those weeks, you have to understand the depth of his resistance to Boltzmann. It was not a casual preference. It was a genuine, long-standing philosophical disagreement about the foundations of thermodynamics, about what the second law actually meant, and whether the universe's tendency toward disorder was a matter of absolute necessity or merely of overwhelming probability. Boltzmann believed in atoms, he believed in statistical mechanics. He had spent his career building a framework in which the second law of thermodynamics, the principle that entropy, disorder, always increases, was a statistical truth rather than an absolute one. In Boltzmann's picture, a gas was made of an enormous number of tiny particles in constant motion, and its bulk properties, temperature, pressure, entropy, were the averaged-out behavior of all those particles. Entropy increases not because the laws of physics forbid it from decreasing, but because the number of ways for a system to be disordered is so astronomically larger than the number of ways for it to be ordered that disorder is overwhelmingly, almost certainly, what happens. It is a matter of probability, not of fundamental law. This is an elegant and powerful idea. It is also, and this was Planck's objection, a picture in which the second law is not truly absolute. In a purely probabilistic universe, there is a technically non-zero chance, vanishingly small but non-zero, that entropy could spontaneously decrease, that disorder could reverse itself, that a scrambled egg could unscramble. Boltzmann accepted this. Planck could not. Planck believed in the absolute, unconditional nature of the second law. He wanted thermodynamics to be a framework built on certainties, not statistics. He had, for years, been skeptical of the atomic picture and the statistical interpretation precisely because it seemed to introduce probability where he wanted permanence. Boltzmann had fought this battle for atoms, for statistical mechanics, for his interpretation of entropy through much of his career against critics who questioned the reality of atoms and the probabilistic foundations of thermodynamics. It was an exhausting fight. Boltzmann died in 1906, only a few years after Planck's breakthrough, never fully vindicated in his own lifetime. And now, in November of 1900, Planck found himself in the uncomfortable position of needing Boltzmann's statistical tool to derive the one formula that fit his data. Boltzmann's method, the one Planck was forced to adopt, involved counting the number of ways energy could be distributed among oscillators. To count arrangements, you need to treat the energy as made up of discrete, countable pieces. You cannot count a continuous distribution. You cannot list the arrangements of something infinitely divisible. To use the combinatorial mathematics that Boltzmann had developed for counting microscopic states, Planck had to divide the energy into units, elements, he called them, and count how many ways those elements could be distributed among the oscillators in the cavity walls. This is the step. This is the moment. In Boltzmann's original application, this was a technical convenience, a mathematical device for counting, after which you took the limit as the size of the energy elements went to zero, recovering the continuous result. The discreteness was a bookkeeping trick, not a physical claim. Planck tried to take the same limit. He tried to let his energy elements shrink towards zero, as Boltzmann had done, expecting to recover a sensible classical result in that limit. But when he took the limit and when he let the size of the energy elements shrink, his formula stopped fitting the data. The match between his equation and the measured blackbody curve depended, crucially, on the energy elements having a specific, non-zero size, a size proportional to the frequency of the oscillator, a size that could not be made arbitrarily small without breaking the agreement with experiment. The energy elements, in other words, had to be real, not a bookkeeping trick, not a counting convenience, something fixed, something finite, something determined by the frequency of the oscillation and by a new constant, a constant of proportionality between frequency and the size of the smallest allowed energy unit. He called this unit the energy quantum, and the constant relating it to frequency is what we now call h, Planck's constant. The relation is this: the energy of a single quantum, a single indivisible packet of energy for an oscillator vibrating at a given frequency, equals h multiplied by that frequency. Written in the shorthand that has since become one of the most recognizable equations in all of physics, E equals h times n, where n is the Greek letter nu, standing for frequency. E chiu teak hin. Let us stay with that for a moment, because the idea itself is not complicated once you hold it gently. Imagine a piano string. It vibrates at a particular frequency, at middle C, say, or whatever note it is tuned to. In the classical picture, you can set that string vibrating with any amount of energy you like. Pluck it softly, it carries a little energy. Strike it hard, it carries more. Energy is continuous. You can deliver any amount in any fine increment, right down to fractions of a joule. There is no minimum unit. There is no smallest step. Now imagine Planck's picture. The string can only vibrate with energies that come in specific steps. 1 quantum, 2 quanta, 3. Whole numbers of the fundamental unit, which is h times the frequency. You cannot give the string half a quantum of energy. You cannot give it 1 1/4 quanta. The allowed energies form a staircase, not a ramp. And the height of each step, the size of 1 quantum, depends on the frequency. Higher frequency oscillators have bigger steps. Lower frequency oscillators have smaller steps. This is a small change to state. It is an enormous change in what it implies. Because if high-frequency oscillators have large energy steps, and if the available thermal energy is limited by the temperature of the cavity, which it is, then at high enough frequencies the steps become larger than the available thermal energy. And if the available energy is less than a single quantum, the oscillator cannot be excited at all. It stays in its ground state, contributing nothing to the radiation. The modes at very short wavelengths, very high frequencies, cannot participate, not because there is anything forbidding them, but simply because the energy required to activate even their smallest allowed step is greater than the temperature of the system provides. They are, in effect, frozen out. This is why the blackbody spectrum has a peak and then falls off at short wavelengths rather than rising forever to infinity. The classical Rayleigh-Jeans catastrophe was built on the assumption that every mode at every frequency could hold any amount of energy down to the tiniest increment. With Planck's quantization, the high-frequency modes are progressively shut down, one by one, as their energy steps grow too large to be paid for from the thermal budget. The spectrum climbs at long wavelengths, peaks in the middle and falls at short wavelengths. The bell-shaped curve, the one that matched the data exactly, and the value of h, the constant that sets the scale of the energy steps, the size of the quantum, Planck calculated from fitting his formula to the experimental data. He found, in those December weeks of 1900, a value for h of approximately 6.626 times 10 to the power of minus 34 joule seconds. Write that out in decimal. 0.222 joule seconds. That is 33 zeros after the decimal point before the significant digits appear. A number so small it is essentially incomprehensible without the scientific notation to compress it. A number so small that in any everyday situation, moving your hand, boiling water, throwing a ball, the discreteness it describes is utterly invisible. The steps in the energy staircase are so tiny, so inconceivably fine, that no human scale measurement could ever detect them directly. Energy appears to flow continuously because the quantum is too small to see. This is why the classical picture worked so well for so long. Newton's mechanics, Maxwell's electrodynamics, classical thermodynamics. They described the world with extraordinary accuracy for every application available in the 18th and 19th centuries. Not because the classical picture was right in its fundamental assumption of continuity, but because the quantum was small enough to be invisible. The grain of reality was hidden in the 33rd decimal place, and yet, the same smallness that hid the quantum from everyday observation also, in the context of the black body problem, made it decisive. Because the PTR experimenters were not measuring everyday energies. They were measuring the distribution of energy across a range of frequencies, including frequencies where the quantum steps were comparable in size to the available thermal energy, where the discreteness mattered, where the classical picture broke, where the freezing out of high-frequency modes was the difference between a sensible finite spectrum and an infinite catastrophe. Planck presented the derivation to the German Physical Society on December 14, 1900. It is the date that historians of science have since marked as the conventional birthday of quantum theory. Planck stood up and explained, carefully and technically, how he had arrived at his radiation formula, the counting, the energy elements, the constant h, the result. The room did not gasp. No one stood up and declared a revolution. The December 14th lecture was a technical paper delivered to an audience of physicists who were interested in the black body problem, and it was received with the polite, measured attention that such papers typically received. There was no dramatic recognition that the world had just changed. No one in that room, perhaps including Planck himself, fully appreciated what the calculation implied. The formula worked, that much was clear. It fit the data. Planck had found the derivation. He had justified the interpolation. He had explained the shape of the curve. But the justification required things that Planck was already uncomfortable with, even as he wrote them down. It required Boltzmann's statistics, the probabilistic counting of microscopic arrangements, the very approach Planck had spent years resisting. In adopting it, he had quietly aligned himself with a picture of thermodynamics he had argued against. He had used the radicals tool, held his nose, and produced a result. He was not pleased by this, but he was honest about it. It required treating the energy elements as real, finite, non-zero quantities, not a counting convenience, but a physical feature of the oscillators themselves, and this was where the discomfort deepened into something more. Because if the energy elements were real, if they were not a mathematical trick to be discarded at the end of the calculation, then energy itself, the fundamental stuff of the physical world, was not continuous. It was discrete. It came in chunks. The smooth, flowing, infinitely divisible picture of energy that underpinned all of classical physics was, in some fundamental sense, wrong. Planck did not state this. He did not announce it. In his December 14th presentation, and in the paper that followed, he introduced the energy elements as the necessary feature of the derivation without drawing the full conclusion about what they implied for the nature of reality. He was a careful man, a precise man, a man who did not rush, to sweeping claims. And he was, underneath all the carefulness, a conservative man, one who had built his career on classical physics and who understood, better than almost anyone, how much of the established framework depended on energy being continuous. What Planck had done was write an equation that worked, and in the process of making it work, he had introduced a constant, a tiny, inconceivably small constant, that carried inside it the seed of everything classical physics was not. He could see the formula, he could verify that it fit, he could follow the derivations step by step, and somewhere in the following days and weeks, as the implications began to settle, he began to feel the weight of what he had put down on paper. The formula was there, the constant was there, the curve matched. And the man who had written it all had used a method he distrusted, produced a result he could not explain away, and introduced into physics a number so small it had 33 zeros in its decimal expansion. A number that was, if you took the derivation seriously, the size of the smallest indivisible unit of energy in the universe. An act of desperation, he would call it, 31 years later, in the letter to Robert Williams Wood. He was ready, he wrote, to sacrifice any of his previous convictions. He needed a theoretical interpretation at any price, however high. The price, as it turned out, was higher than he had imagined when he paid it. He had bought the formula with the continuous world, but in December of 1900, all of this was still ahead of him. He had the equation. He had the constant. He had the derivation. He had presented the result to the German Physical Society in Berlin, and the physicists in the room had nodded and made notes and gone on with their evening. Outside, the century was turning. The old certainties were still largely intact, still glowing with the confidence of Maxwell's equations and Newton's mechanics and the great systematic architecture of 19th century physics. The architecture that Planck had loved, that he had entered the field to understand, that he had been told by Philipp von Jolly all those years ago in Munich, was essentially complete. The formula sat on the page. The constant sat in its place, smaller than almost anything measurable. The question of what it actually meant, what it said about the nature of energy, about the continuity of the physical world, about the foundations that Planck had spent his career building on. That question was not yet answered, and not yet, in most rooms, in most universities, even asked. It would be asked soon enough, and the answer, when it came, would not come from Planck. Let us go back to October, not December, not the derivation, not the night the formula became official, October, and because that is where the real story turns, quieter and more human, in a way that the December date tends to obscure. It was around October 7, 1900, and Heinrich Rubens came to Planck's house. Rubens was one of the experimentalists at the Physikalisch-Technische Reichsanstalt, the precision measurement institute in Berlin, whose meticulous, painstaking work had been slowly, carefully building a picture of black body radiation across the full range of wavelengths. He and his colleague Ferdinand Kurlbaum had been pushing their measurements further into the far infrared, the long wavelength end of the spectrum, where the radiation is too low frequency for the eye to see, where the behavior of the curve is gentle and slow rather than dramatic. And at those long wavelengths, the data told a clear story. Wien's law, the formula that had seemed to work beautifully at the short wavelength high frequency end, simply failed. It predicted the wrong values, wrong enough to matter, wrong enough that no careful experimentalist could overlook it. Rubens told Planck what the long wavelength measurements showed. They talked, as physicists talk, around the problem, around the shape of the curve, around what the data demanded. And that evening, after Rubens had gone, Planck sat with those numbers. Here is what he was working with. On one side, Wien's law. It fit the short wavelengths, the ultraviolet end, but broke at the long wavelengths Rubens had measured. On the other side, the approach that Lord Rayleigh had outlined that same year of 1900, and that Jeans would refine and complete by 1905, the approach built on classical physics, on what is called the equipartition of energy, the principle that in a system in thermal equilibrium, energy distributes itself evenly among all possible modes of vibration. The Rayleigh-Jeans approach, if you followed the classical logic honestly and completely, produced a curve that fit Rubens's long wavelength data rather well. At those gentle, low frequencies, it tracked what was actually measured. That part, the classical theory got right. But follow the Rayleigh-Jeans curve toward shorter wavelengths, toward higher frequencies, toward the ultraviolet, and something terrible happened. The predicted energy density did not level off. It did not peak and come back down the way the measured radiation curve did. It climbed, and it kept climbing, without limit, without ceiling, toward infinity. Classical physics followed faithfully to its conclusion, said that a black body radiating in thermal equilibrium should pour out infinite energy at short wavelengths, not a very large amount, not more than you might expect. Infinite. Every warm object, a glowing piece of coal, a heated cavity, the filament in one of the new electric lamps at the Physikalisch-Technische Reichsanstalt was trying to measure and rate, should, according to the best classical theory available, be radiating an infinite total amount of energy, which it was not, obviously. The coal glowed red, not infinitely. The cavity emitted a measurable, finite, beautifully smooth curve that rose and fell with a clear peak that shifted predictably with temperature. Reality, in other words, disagreed with the classical prediction so profoundly that the disagreement was not a minor correction, it was a catastrophe. Paul Ehrenfest in 1911 would give it a name that stuck, the ultraviolet catastrophe. And the name is apt, though it is worth knowing the name itself came a decade after the fact as a retroactive label for something the physicists of 1900 had already seen and already worried about, without quite having those words for it yet. So Planck had two formulas, Wien's, which worked at one end and failed at the other. Rayleigh's classical approach, which worked at the other end and flew to infinity at the first. And he had Rubens's data, precise and unignorable, showing the full shape of the curve he needed to match. That evening, and through the days that followed, Planck did something that he was very good at, and that is sometimes underappreciated in the telling of this story. He interpolated. He looked at the two formulas, at the two regimes where each worked, and he found a mathematical expression that would smoothly connect them, a formula that reduced to Wien's law at high frequencies and to Rayleigh's classical form at low frequencies, and matched the measured data everywhere in between. He did not derive this formula, he guessed it, a very skilled, very informed, very mathematically sophisticated guess. But still a guess, a curve-fitting exercise, an act of interpolation between known limits. He sent a postcard to Rubens that same evening, giving him the new formula to check against the data. And on October 19, 1900, Planck presented the result to the German Physical Society in Berlin. The formula matched the measurements. Rubens had checked, and it was right, and the audience received it with the polite interest that comes when something works without yet being understood. But Planck knew he had a problem. He had the formula, he did not have the physics. He had found the equation that described the curve, but he had not explained why the curve had that shape, what it said about the nature of radiation and matter and heat. A formula without a physical foundation is not a theory, it is a description. And Planck was a theoretical physicist. The description was not enough, so he went to work on the derivation, and this is where the story becomes strange. To derive his formula, to get from physical principles to the equation he had already written down, Planck found himself forced to make an assumption that went against everything he had professionally believed and personally defended. He he had to turn to Ludwig Boltzmann. Boltzmann was, in a sense, Planck's philosophical opponent. Not personally, they were colleagues, they corresponded, but on a deep question about the nature of the second law of thermodynamics, the law that says entropy increases, that heat flows from hot to cold, that ordered things tend toward disorder. Planck believed the second law was absolute, fundamental, certain in a way that admitted no exceptions and required no probability. The universe moved in one direction in time, and that was that. Boltzmann believed something different. He believed the second law was statistical. It held because the number of ways things could be disordered vastly outnumbered the ways they could be ordered. So, on average, overwhelmingly, systems moved toward disorder. But the second law was, in Boltzmann's view, a statement about odds, not about certainties. In principle, a cup of cold water could spontaneously boil while the surrounding room cooled down. It was just so fantastically unlikely that it would never happen in the observable lifetime of the universe. The second law was probability dressed up as inevitability. Planck had resisted this, had argued against it, in fact, more than once. And now, to derive his own radiation formula, he had to use Boltzmann's counting method. He had to treat the energy of the oscillators in the cavity walls as divided into finite discrete elements, count the number of ways those elements could be distributed, apply Boltzmann's statistical logic, and see what came out. What came out was his formula. Exactly. And the discrete energy element, the thing he had introduced as a mathematical convenience for the counting, the smallest chunk of energy the oscillators could trade, turned out to have a specific value. It was proportional to the frequency of the oscillator, and the constant of proportionality was a new quantity, a number that appeared in the derivation and nowhere before in physics. He called it H. Planck's constant, approximately 6.626 times 10 to the power of negative 34 joule-seconds. To write that number out in full would take 33 zeros after the decimal point before you reached the 6. It is a number so small that it explains in one stroke why the graininess of energy is invisible in ordinary life. The individual packets, the energy elements, the quanta, each one is so vanishingly tiny that when you have trillions of them flowing through a heated wire or a glowing coal, the discreteness is completely washed out. You see a smooth, continuous flow. The grain is there, but H is so small that you will never notice it without instruments of great precision and phenomena where individual quanta make a difference. And the formula for the energy of a single quantum, the smallest amount of energy an oscillator of a given frequency could emit or absorb, was E equals H times N, where N is the frequency. Energy equals Planck's constant times frequency. E equals Hn. That is the equation, the one at the center of this story, not a complicated equation to look at. 5 characters if you count the equals sign. But what it said, what it quietly, almost shyly insisted, was that energy did not flow in a continuous stream. It came in packets, indivisible units. Below a certain size, there was no smaller amount. You could have 1 quantum of a given frequency, or 2 or 3. You could not have 1.5. You could not have a millionth of one. The continuous world, the world of smooth and infinitely divisible quantities that classical physics had assumed without question since Newton, had a minimum unit, a grain, and that grain was so small it had hidden itself from everyone, from every instrument, from every experiment, for the entire history of science, until a precise enough measurement of a glowing cavity in a Berlin institute finally forced it into the light. Planck presented the derivation on December 14, 1900, and so there it was. The formula, written down. The constant, calculated. The energy element, named. December 14th, 1900. You might expect what came next to be celebration. A man who had cracked open the universe, standing at his chalkboard, receiving the astonished applause of colleagues who understood immediately what had been found. That is the story we tell, that is the myth, but the truth is quieter, and in some ways far more interesting. The room did not gasp. There was no collective, sharp intake of breath, no hush of recognition, no colleague leaning over to another and whispering that they had just witnessed the end of one age and the beginning of the next. The German Physical Society noted the presentation in its proceedings. A few people were curious, most moved on. The December 14, 1900 talk drew little immediate notice. The world continued, as it usually does when the ground has actually shifted beneath it, entirely unaware. And Planck himself, the man who had written the equation, was not standing at his chalkboard in triumph. He was standing there in something closer to unease. He had the formula. It worked. It fit every measurement Rubens and Kurlbaum had shared with him, fit the long wavelengths that had broken Wien, fit the short wavelengths where Rayleigh's approach spilled into infinity. The curve was right. The constant was calculated to a value remarkably close to what modern instruments confirm today. By any measure of scientific accomplishment, he had done something extraordinary, but he could not tell you why it was true. He had borrowed Boltzmann's counting method, the method he had spent years quietly opposing, and he had divided energy into discrete elements as a kind of bookkeeping device. And the only way to make the mathematics work, the only way to get a finite, sensible answer instead of an infinite, catastrophic one, was to let those elements stay discrete. Not to smooth them out at the end, not to take the limit that would restore continuity, but to leave them as they were. Permanent packets, an irreducible grain. And that, Planck believed, or desperately hoped, was a problem to be fixed. A scaffolding to be removed once the real foundation was built. He thought he had the answer. He was not sure he believed the answer. So he set to work on the only task that seemed appropriate, trying to derive the same result without the discontinuity. If the quantum was real, someone would have to prove it from first principles, from the deep mechanics of wave and field that he trusted. If it was a trick, a convenience, an artifact of a counting method imported from statistical mechanics, then classical electrodynamics should eventually yield the same result through its own, more rigorous means. For roughly the next decade, from 1900 to around 1911, Planck tried. He attempted multiple reformulations. He proposed variations on the energy element idea that might be compatible with continuous electromagnetic theory. He looked for routes around the discontinuity that would still produce the right spectral curve. He was not lazy about it. He was rigorous, careful, and deeply serious, the way a craftsman is serious about a flaw in his own work that he cannot stop returning to. He kept trying because he could not accept that a mathematical trick was the last word on the nature of reality. He largely failed. Every road led back to the same place. The discreteness would not be argued away. The energy element refused to dissolve back into a continuous flow without the formula dissolving with it. The scaffolding, as it turned out, was also the building. Remove it, and the whole structure came down. But Planck did not know that yet. Or rather, he suspected it increasingly, and found the suspicion uncomfortable rather than exciting. So he kept trying. And while he was trying, a young man in Bern, a patent examiner who had failed to secure an academic position and was doing theoretical physics in whatever time the patent office left him, was looking at the same equation and thinking something very different. Albert Einstein was 26 years old in 1905. He had read Planck's December 1900 paper. He understood what Planck had done, and he understood something that Planck was not yet willing to accept. That the discreteness was not a trick. Einstein took the quantum literally. Planck had used the energy element idea to describe the behavior of oscillators in the cavity walls, the things that emitted and absorbed the radiation. But Planck still thought of light itself as a continuous wave, which is what Maxwell's equations said, and what the whole of classical electrodynamics assumed. The discreteness in Planck's picture was a property of matter, of the tiny oscillators. Light remained continuous. Einstein looked at that and thought, what if it isn't? What if the radiation itself, light itself, also comes in discrete packets? And he wrote a paper. In 1905, the same year he published Special Relativity, the same year he explained Brownian motion, the year that has been called his Annus Mirabilis, his miraculous year. Einstein published a paper proposing that light was not a continuous wave, but was quantized, that it traveled in discrete packets of energy, that each packet carried an energy of h times its frequency. E equals hn, but now applied to the light itself, not just the oscillators. These packets would eventually come to be called photons, though that word came later. And with this hypothesis, Einstein could explain something that had been puzzling physicists for years: the photoelectric effect. When you shine light on a metal, electrons are sometimes knocked free from the metal's surface. Classical wave theory said this should depend on the intensity of the light. A brighter, more powerful wave should knock out more energetic electrons. But that is not what experiments showed. What mattered was not the brightness, but the frequency, the color of the light. Dim violet light knocked out electrons. Bright red light, no matter how intense, did not. Classical physics had no good explanation for this. Einstein's light quantum hypothesis explained it immediately. Each photon carries an energy proportional to its frequency. A violet photon carries enough energy to knock an electron free. A red photon, regardless of how many of them you throw at the metal, does not. Each individual photon simply does not have enough energy. Brightness in classical terms means more photons, but if each photon is too weak, more of them still do nothing. The discontinuous particle-like behavior of light was the only thing that made the observations sensible. Albert Einstein won the Nobel Prize in Physics in 1921. The award citation was specific. It was not for special relativity, the theory that reshaped our understanding of space and time, and that much of the world would say was his greatest achievement. It was for the photoelectric effect, for the discovery of the law of the photoelectric effect, for taking the quantum of energy seriously and showing what it could do. And what did Max Planck, the man whose constant Einstein had borrowed, whose equation had made all of this possible, think of Einstein's light quanta? He did not like it. Planck championed Einstein in other ways. He was one of the people who recognized Einstein's genius early, who fought for him to be taken seriously, who helped him secure a position at the University of Berlin. He admired Einstein greatly. In 1913, Planck wrote a letter recommending Einstein for membership in the Prussian Academy of Sciences, and the letter was glowing. Einstein, he wrote, was one of the most important theoretical physicists of the age. His work on special relativity represented an achievement of the first rank. And then, with the same letter, in the same breath of praise, Planck asked his readers not to hold one thing too much against him, not to judge him too harshly for one particular misstep. One could not expect, Planck wrote, that Einstein would always have hit the target with his speculations, and the specific speculation Planck had in mind, the one he was gently excusing as a youthful error, the one he was asking the Prussian Academy to overlook while recognizing Einstein's brilliance, was the light quantum hypothesis, the light quanta, the photons, the idea that had explained the photoelectric effect cleanly, elegantly, and correctly, the idea that had given Einstein his Nobel Prize. That was the thing in 1913 that Max Planck, the man whose constant underpinned the entire hypothesis, was publicly characterizing as a missed target. Sit with that for a moment if you're still awake enough to sit with anything. The conservative who introduced the quantum, writing in defense of the radical, who extended it, asking the committee to excuse his protege for going too far. The irony would be almost too perfect if it weren't so thoroughly documented. Planck was not being foolish or petty. He had reasons. Maxwell's equations, one of the supreme achievements of classical physics, described light as a wave, and those equations worked extraordinarily well for almost everything: diffraction patterns, interference, the entire technology of optics. The wave nature of light was not a casual assumption. It was among the most well-tested ideas in all of physics. To say that light was also a particle, that it came in discrete packets with definite energies, felt like a step backward to something naive, something pre-Maxwell, something that threw away hard-won understanding. Planck's conservatism had real intellectual backing. He was not wrong to be cautious. He was just, as it turned out, wrong about this particular thing. Meanwhile, the quantum was accumulating weight, the way a snowball accumulates mass rolling downhill. You could not stop it just by wishing it away. In 1911, the physicist Ernst Solvay, a Belgian industrialist with a deep interest in science, funded a conference in Brussels. It was an extraordinary gathering. The invitation list reads like a roll call of the greatest physicists in Europe: Henri Poincaré, Marie Curie, Hendrik Lorentz, Ernest Rutherford, Albert Einstein, Max Planck. The theme of the conference was radiation and quanta. The quantum, in other words, had become serious enough, troubling enough, and important enough to convene the best minds of the age specifically to grapple with it. The 1911 Solvay conference did not resolve the quantum problem, but it did something arguably more important. It made the quantum a collective project. Before Brussels, the discontinuity had been Planck's uncomfortable private guest, Einstein's bold speculation, a handful of puzzles in the data. After Brussels, it was a research program, a shared question that everyone in the room had agreed, whether they liked it or not, demanded attention. The quantum was no longer an oddity. It was the central problem of physics, and Planck sat there in Brussels among his peers, and the equation he had written in desperation 11 years earlier looked back at him from the agenda. He could see it was not going away. He could see the others taking it seriously in ways he had not yet fully allowed himself. But old habits of thought are stubborn things, and Planck was, above all, a man of old habits. Dignified, formal, classically trained, constitutionally unwilling to overturn what he could not fully rebuild. He was getting closer, slowly, reluctantly, the way a careful man approaches the edge of a cliff, not by running, but by degrees, by looking, by measuring the distance with his eyes before he allowed himself to fully believe in the drop. And then in 1913, a young Danish physicist named Niels Bohr took the equation and did something with it that Planck had not done and Einstein had not done, something that finally made the quantum not just a property of radiation, but a property of the atom itself. Bohr was working on the structure of hydrogen, the simplest atom. The problem was this: electrons orbiting a nucleus in classical electrodynamics should continuously radiate energy, losing it in a constant electromagnetic spiral, and fall into the nucleus in a fraction of a second. Atoms, by classical reasoning, should not be stable. And yet atoms are stable. Here was another place where classical physics, taken seriously, predicted a catastrophe the universe had simply declined to experience. Bohr proposed that electrons could only occupy certain specific orbits with specific quantized energies, and that they did not radiate while in these orbits. They only emitted or absorbed energy when they jumped from one orbit to another, and the energy of that jump was exactly equal to h times the frequency of the emitted or absorbed light. E equals Hin again, Planck's constant, turning up at the heart of the atom. The Bohr model of the atom was not the final answer. Later quantum mechanics would revise and deepen it considerably. But it worked astonishingly well for hydrogen. It predicted the spectral lines of hydrogen, the specific frequencies of light that hydrogen emits, with a precision that classical physics could not approach, and it did so by building directly on Planck's energy quantum. The desperate scaffolding had become a foundation. The temporary mathematical trick had now been used to explain the structure of matter itself. The atom was quantized, radiation was quantized, the universe at its smallest scales was not smooth and continuous but discrete and granular, and not just as an abstract philosophical claim, but as a working, predictive, tested piece of physics. By now it was becoming increasingly difficult to maintain that none of this was real. The quantum was explaining too many things in too many contexts with too much precision for it to be dismissed as a bookkeeping artifact. Planck knew this. He was a careful enough scientist to know when the evidence had accumulated past the point of argument. He did not abandon his reservations all at once. That would not have been in his character. But he adjusted. He accepted gradually, and with great reluctance and perhaps a little grief, that the discontinuity was not a temporary scaffolding after all. He had not made a mistake. He had discovered something true. That was perhaps almost harder to accept. And then came the recognition. In 1918, Max Planck received the Nobel Prize in Physics. The citation read, with the careful restraint of the Nobel Committee, that the award was given in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. His discovery of energy quanta. The committee did not say his reluctant and desperate proposal of energy quanta. They did not say his long-regretted introduction of energy quanta. They said his discovery, as though it had been intentional, as though he had set out to find it, had known what he was looking for, and had returned from the hunt with his prize. Planck was 60 years old when the prize was announced. He had watched over the preceding decade and a half as the small and unwanted seed he had planted had grown into something vast. Bohr's atom, Einstein's photons, a generation of younger physicists who spoke fluently in the language of quanta, who did not share his unease with discontinuity, who had grown up with the quantum rather than being ambushed by it late in a career devoted to classical certainties. He accepted the prize, he gave the lecture, he was gracious and precise as he always was, and somewhere in that grace, one imagines, was a complicated kind of peace. Not the peace of a man who had gotten what he wanted, the peace of a man who had let go of what he had expected and was learning, at 60, to look honestly at what he had actually done. He had not wanted to break physics, he had wanted to repair it, he had wanted to find the small correction, the elegant adjustment that would smooth out the rough edge in the data and restore the classical edifice to its perfection. And instead, in doing so, he had discovered the rough edge was load-bearing, that the imperfection was fundamental, that the continuous, smooth, deterministic world of Newton and Maxwell, the world he had loved and chosen to spend his life in, had a crack running through it, and the crack was not a flaw in our understanding. It was the architecture of reality itself. That is what h is. That tiny number, 6.626 times 10 to the minus 34 joule seconds, the number with 33 zeros after the decimal point, is the crack, the grain, the minimum, the place where smoothness stops. Planck did not cause the universe to be quantized. He discovered that it was, and his discovery was so alien to everything he had believed that his first response was to try to erase it. And he spent 10 years doing so. And he failed. And the failure was the proof. He was 65 when a younger generation of physicists, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Niels Bohr still at the center of it, built quantum mechanics proper in the 1920s. The full theory, not the early patches and models, but the deep mathematical framework that describes how reality behaves at the scale of atoms and smaller. Planck watched it happen. He understood some of it and not all of it, the way a composer who wrote a seed melody might understand the symphony that grew from it, recognizing his theme in the larger structure, wondering at what other hands had made of it. The last years of his life were marked by losses that make the mind go quiet. His first wife, Marie, had died in 1909. He had married again, a woman named Marga, and there was some warmth there, some continuation of ordinary life. But the losses kept coming. His son Karl died in action in the First World War in 1916. Then in 1917, his daughter Greta died in childbirth. And the following year, 1919, the same year he received the Nobel Prize, his other daughter Emma died in childbirth as well. Greta and Emma, twins, both gone within 2 years of each other, each at the moment of new life. He endured. That word, endured, appears in descriptions of Planck more than almost any other. It is not quite the same as thrived or flourished or prevailed. It is a quieter word, a harder one. A man who had given his life to finding the eternal and unchanging truths of the universe, who had built his career on the conviction that physics was the pursuit of absolute certainties, now knew that certainty was a thing the universe rationed very carefully. He went on working, he lectured, he served as the secretary of the Prussian Academy of Sciences, and later, after the rise of the Nazis, faced the impossible position of a man who despised a regime and yet was too old, too rooted, and too committed to German science to leave. He stayed. He tried, within the limits of his position and his temperament, to protect Jewish colleagues, and largely failed because the forces arrayed against him were not the kind that yield to dignity and reasoned argument. His friend and admired colleague Einstein left Germany in 1933 and never returned. Planck, at 75, stayed. He endured. And then in 1945, in the final weeks of the war, his son Erwin was executed. Erwin had been involved in the July 20th plot, the attempt to assassinate Adolf Hitler. The plot failed. The reprisals were swift and merciless. Erwin Planck was arrested, tried, and killed. Max Planck was 87 years old when he lost his last surviving son. He had outlived his first wife, 2 daughters, 2 sons from his first marriage. He had watched the country he loved descend into catastrophe. He had watched the classical physics he revered transformed beyond recognition. And still, he lived. He died on October 4th, 1947 in Göttingen. He was 89 years old. If you measure a life only by its discoveries, by the single equation, the constant, the Nobel Prize, you get a picture that is correct but incomplete. Planck was a man whose life contained the full weight of the 20th century. The wars, the losses, the political catastrophe, the scientific revolution he had accidentally started. He carried all of it, and he carried it with a kind of stoic, upright, slightly formal dignity that seems, in retrospect, both admirable and a little heartbreaking. The posture of a man who had been told, early and deeply, that the universe was governed by eternal laws, and who had spent his entire life learning, one hard lesson at a time, that the universe was governed by something both more and less than that. Something stranger, something smaller, something hidden at the bottom of the world, in a number with 33 zeros. Here is what I want you to carry with you as you drift towards sleep tonight, and I hope you are drifting. I hope the lamp is dimming and your breath is deepening and none of this feels too urgent. Think about what the quantum actually means, not the mathematics of it, not the formula, just the thing itself. Before December 1900, the world was, in principle, infinitely divisible. You could always take any quantity, energy, position, time, and imagine cutting it in half. And half again. And half again, infinitely, without ever reaching a bottom. There was no floor. The universe in that picture was smooth all the way down. And what Planck found, what he found while trying to fix a discrepancy in a curve, while trying to explain why glowing objects emitted light the way they did, while using a mathematical trick he borrowed from a man whose philosophy he opposed, was the floor. The minimum. The point at which the universe stops dividing and says, no further. This is the smallest piece. This is where smoothness ends and discreteness begins. That is not a small discovery. It is not a piece of trivia about a 19th century lamp testing institute. It is a statement about the deep nature of reality. That reality has, at its most fundamental level, a grain, a pixel size, a quantum, and that pixel size is H. Planck's constant, 6.626 times 10 to the minus 34 joule seconds. The number so small it hid from everyone for the entire history of science until a precise enough question was asked in a precise enough place. Right now, wherever you are, and I am thinking of you there, in whatever corner of the world you have settled into for the night, you are made of atoms. Your atoms are made of electrons and nuclei. Your electrons occupy specific, quantized energy levels. When they jump between levels, they emit or absorb light at specific, quantized frequencies. Every breath you take, every photon that strikes your closed eyelids, every electrical signal moving through your nervous system right now, all of it operates according to rules that include H. You are not separate from the quantum world. You are thoroughly, irreducibly in it. The classical world, the smooth, continuous, infinitely divisible world that Newton mapped and Maxwell electrified and that Planck devoted his youth to understanding, is not wrong exactly. It is an approximation. A very, very good approximation for large things, for slow things, for the everyday world of candles and kettles and lamp filaments. But underneath it, always, at every scale small enough to matter, the world is granular. It is made of quanta. And that fact was first written down in a kind of anguish by a conservative classical physicist who did not believe it and spent the next decade trying to prove himself wrong. There is something quietly remarkable about that. Not just the physics, but the human shape of it, that the universe waited for precisely this kind of person, careful, rigorous, reluctant, deeply respectful of the existing order, to force out its deepest secret. A bolder, more revolutionary temperament might have proposed the quantum with confidence and had it dismissed as speculation. Planck proposed it as a minimum viable patch, with his head down and his hands shaking a little, and because it was so modest and so mathematical and so precisely tied to real experimental data, it stuck. His caution was the delivery mechanism. His conservatism was why it worked. The man who did not want to overturn physics overturned it precisely because he was too careful to overstate what he had found. He told Robert Williams Wood in that 1931 letter that it had been an act of desperation, that he had been ready to sacrifice any of his previous convictions because a theoretical interpretation had to be found at any price, however high, and he had paid the price, though he had not known it at the time. The price was the smooth world, the continuous world, the world of eternal certainties he had chosen physics in order to inhabit, and what he received in return was something better, if stranger. A true picture of the world. Not the tidy, clean, fully mapped world that Philipp von Jolly had described to him as a young student. The world nearly finished, needing only minor details. But the real world, which is weirder and more textured, and more surprising than anyone in 1858 when Planck was born, had imagined or guessed. You remember where we began tonight, don't you? Or perhaps you have already drifted past the beginning and you are somewhere quieter now, somewhere where the exact sequence of facts has softened into a feeling, which is exactly how this kind of story is supposed to land. We began with a confession. A man writing a letter 30 years after the most important equation of his life to a colleague named Robert Williams Wood, describing what he had done in those December weeks of 1900 as an act of desperation. We began with the paradox of a man who chose physics because he thought its great truths were eternal and settled, and who ended up being the one to show they were not. We began with a number so small it contains the revolution inside its own smallness. And that is where we end, too, with H. With the grain of reality. With the reluctant man who found it. You don't need to hold the formula in your mind as you fall asleep. You don't need to remember the dates or the names, though they are beautiful names and the dates have a kind of poetry, and if some of them surface in a dream, I would not find that surprising. What you might carry, if you carry anything, is just this. The universe is not infinitely smooth. It has a smallest unit of action, and that unit has a name, and a human being discovered it by accident while trying not to, and spent the rest of a long and difficult and serious life making peace with what he had found. That is a good thing to know. It is a good thing to carry into sleep. If you enjoyed this slow journey tonight, this wander through Berlin in 1900, through Planck's study and his laboratory and his long, careful, reluctant mind, a gentle like or a quiet subscribe would mean a great deal to this small channel. I am one person telling one story at a time, and small creators like me genuinely rely on your support to keep these going. It is a small thing and a kind one, and I thank you for it if you choose it. And wherever you are listening from tonight, whatever city, whatever room, whatever hour the clock is showing in your corner of the world, I hope this found you somewhere warm and still. I hope the questions are quieter now than when we started. I hope the universe feels, if anything, a little more extraordinary and a little less frightening than it did before. The quantum will still be here when you wake. The constant will still be written into the fabric of every atom in the room around you. Max Planck, the reluctant revolutionary, will still have found it and refused to believe it, and has spent 10 years trying to unfind it and failed, and accepted and endured. Sleep well, fellow voyager. The next journey keeps until you wake.